Okay. So one of the classifications of reactions, if you see, in terms of reversibility, how many types of reactions we have? In terms of reversibility, we have two types of reactions. In terms of reversibility, we have two types of reactions. One is irreversible reaction, another one is reversible reaction. Irreversible reaction, next one, reversible reaction. Irreversible reaction, the name itself indicates. So it occurs in how many directions? And irreversible reaction occurs in how many directions? Only one direction. It occurs in only one direction. It occurs in only one direction. It proceeds only in one direction. Reversible reaction, it occurs in two directions, forward direction and backward direction. Reversible reactions occurs in two directions, in forward direction and backward direction. Okay. So chemical equilibrium we get in the case of irreversible reactions or reversible reactions. In the case of reversible reactions, we will get chemical equilibrium. Okay. So chemical equilibrium, ionic equilibrium we have. Okay. We have ionic equilibrium also. What is the difference, Andy? In the case of chemical equilibrium, reactants and products involved are generally molecules. Reactants and products involved are molecules. In the case of ionic equilibrium, there exists an equilibrium between molecules and ions. H2O is in equilibrium with H++ OH minus. So their ions are involved in the equilibrium. That is ionic equilibrium. Generally here, which are involved, and molecules are involved under equilibrium. Okay. Next one. So by studying chemical equilibrium, okay, what is the importance of chemical equilibrium? Which information we can get from chemical equilibrium? Okay, the information we get is what are the various factors affecting equilibrium that we study, and what we study under chemical equilibrium topic. If you see, what are the factors that affect chemical equilibrium, also called as reaction equilibrium? What are the factors affect chemical equilibrium? The various factors that may affect chemical equilibrium are pressure, concentration, temperature, catalyst, etc. So they may affect chemical equilibrium. How they may affect chemical equilibrium? Okay, that we study under this topic based on Le-Chatelier's principle. And one of the important concepts from chemical equilibrium, that is Le-Chatelier's principle. So Le-Chatelier's principle explains how these factors affect chemical equilibrium. Okay. So if you increase the pressure, whether it proceeds in the forward direction or backward direction. If you are increasing the concentration, it proceeds in the forward direction or backward direction. Such information we can get. And okay. Next one. What are the conditions to be followed? And what are the conditions to be followed? What are the conditions to be followed to increase the yield of desired product? What are the conditions to be followed to increase the yield of desired product? Okay, desired product. So to increase the percentage of yield of desired product, whether we have to increase the pressure or we have to decrease the pressure, we have to increase the temperature or we have to decrease the temperature, at which temperature and which pressure, okay, under which conditions we get maximum yield of desired product, that also we can explain based on Le-Chatelier's principle. And okay, next, based on equilibrium constant, for chemical equilibrium we calculate what? Equilibrium constant we calculate. By using that equilibrium constant value we can give whether product's concentration is dominating or reactants concentration is dominating. That also, such information also we can get. Okay, so the reaction proceeds in which direction, such information we can get. Okay, what are the various factors that affect equilibrium, that such information we can get. And what are the conditions we have to follow to get maximum yield of desired product. Okay, next one. So in case of irreversible reaction we will get, or in the case of reversible reaction we will get. And in case of reversible reaction we will get chemical equilibrium. So I am taking a reversible reaction, right? Consider a reversible reaction. Consider a reversible reaction. So I am taking a reversible reaction like this. General reaction AAA plus BB. So this proceeds in forward direction and in backward direction. It proceeds in forward direction and backward direction. Let us consider the rate constant for forward reaction Kf. F indicates forward reaction. And let us consider rate constant for backward reaction, that is Kb. So we know in the beginning only forward reaction occurs, and after some time backward reaction takes place, and after some time what happens? Rate of forward reaction becomes equal to rate of backward reaction. Such situation is called what? Chemical equilibrium. Okay, so therefore at equilibrium what happens? And rate of forward reaction becomes equal to rate of backward reaction. At equilibrium, rate of forward reaction is equal to rate of backward reaction. So after reaching equilibrium, whether reaction occurs or cannot occur, even after reaching equilibrium, reaction takes place. Okay, both forward reaction occurs and backward reaction also occurs, but with the same rate. So after reaching equilibrium, is there any change in the number of moles of ABCD, or no change in the number of moles of ABCD? No change in the number of moles of ABCD, since both forward reaction and backward reaction occurs at same rate. Reaction occurs but no net reaction. Okay, such situation is called chemical equilibrium, or that is called dynamic equilibrium. So measurable properties cannot change with time. If measurable properties cannot change with time, such situation is called dynamic equilibrium. Okay, so even though reaction occurs, properties cannot change. Okay, how to give rate of a reaction? Rate of a reaction is equal to rate constant into, okay, according to law of mass action we have, that we will discuss in detail in chemical kinetics. According to law of mass action, rate is proportional to what? Rate is proportional to product of concentrations of reactants. And product of concentrations of reactants raised to the powers. The powers are nothing but stoichiometric coefficients present in the balanced equation. If you remove the proportionality, we will get a constant that is called as what? Rate constant. So rate of a reaction is equal to rate constant into product of concentrations of reactants raised to the powers. The powers are nothing but what? Stoichiometric coefficients present in the balanced equation. So therefore forward reaction, what is rate constant? And Kf into product of concentrations of reactants, that is concentration of A into concentration of B raised to the powers. Powers are nothing but stoichiometric coefficients present in the balanced equation. A power A, B power B. Similarly, rate of backward reaction. What is rate constant for backward reaction? Kb. What are the reactants for backward reaction? C and D. Their stoichiometric coefficients. C power C, D power D. So like this we can give rate of forward reaction and rate of backward reaction. Rate constant into product of concentrations of reactants raised to the powers. Powers are nothing but their stoichiometric coefficients. Now if you take the ratio of forward rate constant to backward rate constant, ratio of forward rate constant to backward rate constant, we get C power C, D power D, by A power A B power B. So the ratio of forward rate constant to backward rate constant is called as equilibrium constant. That is another constant. This is rate constant, this is rate constant. Their ratio is another constant. That new constant is called as equilibrium constant. This is equilibrium constant with respect to concentrations, and here we are writing with respect to concentrations. That's why it is denoted as Kc. We are writing equilibrium constant with respect to concentrations, so that is denoted as Kc. So this is the formula for Kc, equilibrium constant. C power C D power D by A power A B power B. Now, if you consider reactions involving gases, and if you consider reactions involving gases, so for the reactions involving gases, we express concentration with respect to what? Pressure. We express their concentration with respect to pressure, and so we get the equilibrium constant with respect to pressure. Equilibrium constant with respect to pressure is given as Pc power C Pd power D by Pa power A into Pb power B. This is equilibrium constant with respect to what? Pressures. If A, B, C, D are gases, and if A, B, C, D are gases, okay, then we give equilibrium constant with respect to pressure like this. Concentrations we can express with respect to pressures. Here Pi is called as partial vapor pressure. Here Pi is called as partial vapor pressure. For example, Pc, partial vapor pressure of gas C, partial vapor pressure shown by gas C, and Pa, partial vapor pressure shown by gas A. How to give partial vapor pressures, and how to give partial vapor pressures? By using Dalton's law. According to Dalton's law of partial vapor pressures, Pi is equal to what we have? P total into its mole fraction. Its mole fraction in the liquid phase or gas phase? Gas phase. According to Dalton's law, we can give partial vapor pressure as total vapor pressure into its mole fraction in the gas phase. Okay, so we took a reversible reaction. From that we derived the expression for equilibrium constant, which is nothing but forward rate constant by backward rate constant. This is Kb and not Kc. Kf by Kb, which is nothing but forward rate constant by backward rate constant. Okay, that we express with respect to concentrations and with respect to pressures. Generally, for the reactions involving gases, we proceed with respect to pressures. Okay. Next, if you see the relation between Kp and Kc, and relation between Kp and Kc. I am giving direct equation that we can get by using ideal gas equation. Let us consider gases behave ideally. If gases behave ideally, then PV is equal to, we can write as nRT. PV we can write as nRT. So from in the place of P, if you write nRT by P, then finally we will get, okay, finally the relation is Kp is equal to Kc into RT whole power delta N. Kp is equal to Kc into RT whole power delta N. And this is the relation we have, where delta N is equal to, okay, here we are using ideal gas equation. And okay, so we have to concentrate on number of moles of gaseous substance, and we have to concentrate on gaseous substance. So delta N is number of moles of gaseous substance towards product side minus number of moles of gaseous substance towards reactant side. So by using ideal gas equation, we converted from pressure terms to concentration terms. Okay. For example, if you take N2 gas plus 3 moles of H2 gas, then equilibrium with 2 moles of ammonia gas. So for this reaction, what is the relation between Kp and Kc? For this reaction, what is the relation between Kp and Kc? What is delta N and E? Product side, how many moles of gaseous substance we have? 2. Reactant side, 3 and here 1. 3 and 1. So that is 4. So therefore delta N value minus 2. So the relation between Kp and Kc is from equation 1. Let us consider that is equation 1. So from 1 we can give as Kp is equal to Kc into RT whole power minus 2. Okay. Kp is equal to Kc into RT whole power minus 2. For example, if you have a reaction like this, and PCl5 gas undergoes dissociation to give PCl3 gas plus Cl2 gas. So what is the relation between Kp and Kc for that reaction? What is delta N value? And product side, how many moles of gaseous substance we have? 2. 1 plus 1. Reactant side 1. So delta N value is 1. So therefore from 1 we can write Kp is equal to Kc into RT whole power delta N. Delta N value is 1. Kp is equal to Kc into RT. Sometimes they are asking what is Kp by Kc value. Kp by Kc is equal to here 1 by RT power 2. Here Kp by Kc is equal to what? RT. Okay. Previously in set exam like that they given, and gate exam also once a question given. They given equation and they asked what Kp by Kc value. The expression for Kp by Kc. And finally, if you take a reaction like this, and for this, what about delta N and E? Product side we have 2 moles, reactant side also we have 2 moles. Product side 2 moles, reactant side also 2 moles. So delta N value 0. So therefore from 1 we get Kp is equal to Kc into RT whole power 0. RT whole power 0, something power 0 is 1. So therefore Kp is equal to Kc. Right. So this is the relation between Kp and Kc. Just you remember this equation. Kp is equal to Kc into RT whole power delta N. Okay. Next, and put a note. For example, I am taking a reaction like this, and I am taking a reversible reaction. A plus B is in equilibrium with C plus D. For this, equilibrium constant means ratio of forward rate constant to backward rate constant. For example, I am giving as K1, and equilibrium constant I am giving as K1. Now if you take reverse reaction, if you take reverse reaction, that is C plus D is in equilibrium with A plus B. For this I am taking equilibrium constant as K2. Then what is the relation between K1 and K2? What is the relation between K1 and K2? K1 is equal to K2. I wrote reverse, and K1 is equal to 1 by K2, or K2 is equal to 1 by K1. And okay, K2 is equal to, both are inverse to each other. And okay, for example, if you write the expression for K1, K1 means what? Product of product side concentrations by product of reactant side concentrations. So we get K1 C into D by A into B. Okay, powers stoichiometric coefficients given only one. Similarly, K2, what is the expression for K2 andi? Product side concentrations andi, that is A into B by C into D. So therefore K2 is equal, this is nothing but inverse of this or not? Okay, AB by CD, that is inverse of CD by AB, that means K2 is equal to what? 1 by K1 andi. So therefore if reaction 2 is equal to reverse of reaction 1, then what is the relation between their equilibrium constants andi? Both are inverse to each other. If you take reverse of a reaction, then equilibrium constant will get inverse andi. Okay, this is first case. Next case I am giving. For example, I am taking a reaction like this. A plus B is in equilibrium with C plus D. For this, I am taking equilibrium constant as K1 andi. Okay. For that, I am taking equilibrium constant K1. So now I am multiplying the above equation by n andi. I am multiplying the above equation by n. So then what we get? NA plus NB gives rise to NC plus ND. I am multiplying the above equation by n. NA plus NB gives NC plus ND. Okay. For this I am taking equilibrium constant as K2. Now what is the relation between K1 and K2? If you multiply a reaction by n, then what happens to equilibrium constant? NK2. K2 is equal to K1 by n. K2 is equal to K1 power n we will get. And K2 is equal to what we get? K1 power n. Okay, if you write the expression for K1, what is the expression for K1 andi? Product side concentrations by reactant side concentrations. And if you write for K2 andi, K2 what we get? C power n D power n product side concentrations by A power n B power n. So this can be written as CD by AB whole power n. CD by AB whole power n. But what is CD by AB? CD by AB is nothing but K2. So sorry, K1. So K2 is equal to what? K1 power n. So if a reaction is multiplied by n, okay, then the relation between those two equilibrium constants, K2 is equal to K1 power n. I am giving next case andi. For example, we have third case. A plus B gives C plus D. C plus D gives E plus F. A plus B gives C plus D. C plus B gives E plus F. For this, equilibrium constant is K1 andi. And for this, equilibrium constant is K2. If you add these two andi, if you add these two, reaction 1 plus reaction 2, if you add those two reactions, what we are getting? A plus B is in equilibrium with E plus F. So for this I am taking equilibrium constant as K3. Then what is the relation between K1, K2 and K3? Okay, we are getting third reaction by adding first reaction and second reaction. Reaction 3 is obtained by adding reaction 1 and reaction 2. Then what is the relation between these three? And K3 is equal to K1 into K2 we will get. And K3 is equal to K1 into K2. So how we get, if you see, if you write the expression for K1, CD by AB. If you get the expression for K2, That is, what is the expression and EF by CD, and if you take the expression for K3, EF by AP. Okay, write the expressions for K1, K2 and K3. Now what about K1 into K2? If you do K1 into K2, CD gets cancelled. CD gets cancelled. So we get EF by AB. Okay, if you do K1 into K2, CD gets cancelled. We get EF by AB. What is EF by AB? And that is K3. EF by AB is K3. So therefore the relation between K1, K2 and K3 is K3 is equal to K1, K2. Okay. For example, reaction 1 plus reaction 2 plus reaction 3 gives fourth reaction. Then what is the relation between K1, K2, K3, K4? K4 is equal to K1 into K2 into K3. And right. And one more case we have. Next case, I am taking first reaction like this. A plus B is in equilibrium with C plus D. A plus B is in equilibrium with C plus D, for which equilibrium constant is K1. Second one, E plus F gives C plus D, for which I am taking equilibrium constant as K2. I am taking two reactions like that. Now if you do 1 minus 2 and if you do 1 minus 2, what we get? CD gets cancelled. Here we get minus E minus F, that if you bring right side. So finally we get what? A plus B gives E plus F. CD gets cancelled. A plus B gives E plus F, that we are getting. For this I am taking equilibrium constant K3. For that I am taking equilibrium constant K3. Now what is the relation between K1, K2 and K3? And K3 is equal to K1 by K2. K3 is equal to K1 by K2. So write the expressions for K1, K2, K3 and K1 C into D by A into B, K2 CD by EF. Write the expressions for K1, K2, K3 and EF by AB. Okay, CD by AB, CD by EF and K3 EF by AB. Now how we get K3 and how we get K3? If you do K1 by K2, if you do K1 by K2, K1 is CD by AB, K1 is CD by AB. Okay, 1 by K2, 1 by K2 means we get EF by CD, EF by CD. So CD gets cancelled. We are getting what? EF by AB. EF by AB is nothing but what? K3. So just you remember the final conclusions. Okay, so we are getting K3 is equal to K1 by K2. So if reaction 1 minus reaction 2 gives reaction 3, then K3 is equal to, we have K1 by K2. So these are the various cases we have. Previously 4 marks questions also given and in CSIR from these expressions. Okay. So once if you see the conclusions, for example, if you have reaction 2 is equal to reverse of reaction 1. For this equilibrium constant is K2. For this equilibrium constant is K1. For reaction 1 equilibrium constant is K1. For reaction 2 equilibrium constant is K2. What is the relation between those two? Both are inverse to each other. So K2 is equal to 1 by K1. Okay. Final conclusions I am giving. Next one. If reaction 2 is equal to N into reaction 1. For reaction 1 equilibrium constant K1. For reaction 2 equilibrium constant is K2. Then what is the relation between K1 and K2? K2 is equal to K1 power N we have. K2 is equal to K1 power N. Next, if you have like this, reaction 1 plus reaction 2 gives reaction 3. For this we have K1, for this we have K2, and for this we have K3. What is the relation between K1, K2, K3? K3 is equal to K1 into K2. Okay. Next, if reaction 1 minus reaction 2 gives reaction 3. If reaction 1 minus reaction 2 gives reaction 3, what is the expression we have? K3 is equal to have K1 by K2. K3 is equal to have K1 by K2. Okay. For example, I am giving like this. N1 reaction 1 plus N2 reaction 2 gives reaction 3. N1 into reaction 1 plus N2 into reaction 2 gives rise to reaction 3. Then what is the expression for K3 and for reaction 1 we have K1 and for reaction 2 we have K2. For reaction 3 we have K3. K3 is equal to K1 power N1 into K2 power N2. So K3 is equal to K1 power N1 into K2 power N2. Here we will get product. While we are adding, we will get product. And while we are multiplying with N, we will get power. While we are multiplying with N, we get power. So therefore, N1 into reaction 1 means K1 power N1 we will get. N2 into reaction 2 means K2 power N2. So we will get K1 power N1 into K2 power N2. For example, we are getting like this. Reaction 1 minus reaction 2 gives reverse of reaction. Reaction 1 plus reaction 2 gives reverse of reaction 3. Reaction 1 plus reaction 2 gives reverse of reaction 3. If reaction 1 plus reaction 2 gives reaction 3 directly, then what is the formula we have? K3 is equal to K1 into K2. But if you get reverse then we get 1 by K1 into K2. Okay, reverse means what we have to take? Inverse we have to take. So in such case we get K3 is equal to 1 by K1 into K2. Okay, for reaction 3 we have K1 into K2. Reverse we are getting. So therefore we get 1 by K1 into K2. Okay. So next one, Andy. We have to see the importance of equilibrium constant. Here what we are calculating, and equilibrium constant we are calculating. Okay, that is nothing but ratio of forward rate constant by backward rate constant. Okay, or product side concentrations by reactant side concentrations. For reactions involving gases we follow pressures. Okay, once if you know K value, Okay, what is the data we can get and what is the importance of K? Put the heading importance of equilibrium constant. Importance of equilibrium constant. Importance of equilibrium constant. Okay. Once we know equilibrium constant is equal to what? Product side concentrations by reactant side concentrations. Equilibrium constant is what? Product side concentrations by reactant side concentrations. Once if you know K value, okay, if K value is high, if K value is very high, that indicates that products concentrations are high or reactants concentrations high. Products concentrations are high. That means products are dominating over reactants and okay, reaction proceeds in the forward direction and okay. If K value is very low, that indicates that reactants concentrations dominate over product concentration and so based on K value we can give what? Whether products concentration is dominating or reactants concentration is dominating during a reaction. Write that point. If K value is high, if K value is high, if K value is high, products dominate over reactants. If K value is high, products dominate over reactants. Next, if K value is low, if K value is low, if K value is low, reactants dominate. If K value is low, reactants dominate over products. If K value is low, reactants dominate over products. For example, I am giving K values for dissociation of nitrogen oxides and okay, dissociation of nitrogen oxides, oxides of nitrogen. For example, if you take dissociation of various nitrogen oxides, I am giving K values like this. And for example, various nitrogen oxides, NO we have, for example, next NO2, N2O5. Okay, for example, these are the nitrogen oxides I am taking. And okay, we are taking what? Dissociation. Okay, K values are like this, equilibrium constant values. K values are like this. For example, here it is 2 into 10 power 5. Okay. For example, it is 3 into 10 power minus 5. For example, it is 5 into 10 powers 8. For example, dissociation, equilibrium constant values are like this. And for example, equilibrium constant values are like this. Now tell me which is the stable nitrogen oxide. According to the data given, what is the stable oxide of nitrogen? What is the stable oxide of nitrogen? What is the stable oxide of nitrogen? NO or NO2 or N2O5? NO2. NO2. For NO2, K value is very high. K value very high means products dominate or reactants dominate? Products dominate. So that can undergo easily dissociation. That can undergo easily dissociation. That means its oxide is not stable. Its oxide is not stable. Products are stable. Okay, therefore, for which one K value is low only? For N2O5 K value is low. K value is low means it is not undergoing readily dissociation. Here reactants are dominating. That means which is stable oxide only? N2O5 is the stable oxide of nitrogen according to the data given. And according to the data given, N2O5 is the stable oxide of nitrogen. So like this we can give whether products dominate or reactants dominate based on K values. And another advantage is once K value is known to us, once K value is known, okay, K is equal to what? Product side concentrations at equilibrium by reactant side concentrations at equilibrium. Product side concentrations at equilibrium by reactant side concentrations at equilibrium. So if K is known to us, we can calculate equilibrium concentrations of reactants and products. And later we'll discuss a problem for this. Okay, so if K is provided to you, what we can calculate? Equilibrium concentrations of reactants and products. And so write that point. Once K value is known, we can calculate equilibrium concentrations of reactants and products. Once K value is known, we can calculate equilibrium concentrations of reactants and products. Okay. So next one more application is by comparing K and Q. What is Q and reaction quotient? By comparing equilibrium constant and reaction quotient, we can give the direction of reaction, whether reaction proceeds in the forward direction or backward direction, or it is under equilibrium. Such information we can give by comparing what? K and Q. Write that point. By comparing K and Q, we can predict the direction of equilibrium, the direction of reaction, right? We can predict the direction of reaction, whether it proceeds in forward direction or backward direction or under equilibrium, that we can predict. Okay, if you have a reaction like this, what is the expression for equilibrium constant and what is the expression for reaction quotient? Okay, Q is called as what? Reaction quotient. What is the expression for these two? Both have same expressions. Both have same expressions. Both have same expressions, but the difference is in equilibrium constant we substitute the concentrations of A, B, C, D at equilibrium only. Here we can substitute the concentrations of A, B, C, D at any stage of the reaction. During progress of reaction, what happens to the concentrations of A, B, C, D? Remains same or changes? Same. Remains changes up to appearance of equilibrium. Concentrations of A, B, C, D changes. That means Q value also changes. But here we have to substitute which concentrations? Only equilibrium concentrations. After reaching equilibrium, concentrations of A, B, C, D changes or doesn't change? Doesn't change. That means Kc value doesn't change. Okay. So during progress of reaction, what happens? Q value changes, but K is fixed. Q value changes, and when reaction reaches equilibrium, Q value reaches K value. Q value approaches K value. So K is a special case of Q. K is a special case of Q. Okay, during progress of reaction, A, B, C, D concentrations changes, so Q value also changes. But after reaching equilibrium, A, B, C, D concentrations doesn't change, so K value is fixed. So during reaction, what happens? K value changes and finally reaches what? K value. Okay, so K is a special case of Q. Okay, next one. So by comparing Q and K, we can give the direction of reaction. For example, if Q is less than K, if Q is less than K, that indicates the reaction proceeds in the forward direction or backward direction. Q value less than K means still equilibrium concentrations of C and D not formed. Still equilibrium concentrations of C and D are not formed. That means it proceeds in which direction? Forward direction. Okay. It proceeds in the forward direction. Then C, D concentrations increases, Q value increases and approaches K value. Okay. If it proceeds in the forward direction, what happens? CD concentration increases, so Q value increases and reaches what? K value. Okay. If Q is less than Kc, reaction proceeds in forward direction. If Q is greater than K, then reaction proceeds in which direction? Backward direction. Concentrations of C and D is more compared to equilibrium concentration. So concentrations of C and D to be decreased and Q value to be decreased up to appearance of equilibrium. Q value decreases and up to equilibrium. It finally reaches what? K value. Okay, reaction proceeds in backward direction here up to appearance of equilibrium. In the previous case also, if Q is less than Kc, reaction proceeds in backward direction up to appearance of equilibrium. That means up to Q value becomes equal to K value. If Q is equal to Kc, then it indicates that reaction is at equilibrium. Reaction is at equilibrium. So by comparing Q and Kc, we can predict the direction of reaction, whether it proceeds in forward direction or backward direction or under equilibrium. Such information we can get. For both the equations are same, only the difference is Q means at any stage, K means only at equilibrium. Right. Okay, now we see some questions and based on these points. Right. Okay, this is the question given in CSIR for 4 marks. First reaction, CO gas. First reaction is CO gas plus H2O gas gives CO2 gas plus H2 gas. Comma, equilibrium constant is equal to K1. Equilibrium constant is equal to K1. Second reaction, CH4 gas plus H2O gas CO gas plus 3 moles of H2 gas. 3 moles of H2 gas. Equilibrium constant is equal to K2. Equilibrium constant is equal to K2. Third one. Continuation, you write. Continuation. The equilibrium constant for the reaction. The equilibrium constant for the reaction. The equilibrium constant for the reaction. CH4 gas plus 2H2O gas. The equilibrium constant for the reaction CH4 gas plus 2H2O gas gives CO2 gas plus 4 moles of H2 gas the equilibrium constant for the reaction is options given K1 plus K2, K1 minus K2, K1 into K2, K1 by K2. Direct question given. How we are getting third reaction? And by adding reaction 1 and reaction 2. If you add reaction 1 and reaction 2, CO gets cancelled, CO gets cancelled, CH4 plus H2O plus H2O 2H2O, CO2 plus H2 plus 3H2 4H2. That means we are getting reaction 3 by adding reaction 1 and reaction 2. If reaction 3 is equal to reaction 1 plus reaction 2, then K3 is equal to what we have? K1 into K2. K1 into K2. That is option 3. And the same question given in different way and for 4 marks. Similar type of question. CH4 gas plus 2H2O gas gives CO2 gas plus 4 moles of H2 gas, equilibrium constant K1, CO gas plus H2O gas, CO2 gas plus H2 gas. Equilibrium constant is K2. The equilibrium constant for the reaction, CH4 gas plus H2O gas, CO gas plus 3H2 gas is okay. Once again, for 2 reactions equilibrium constant is given. Third reaction we have to calculate it. Options K1 by K2, K2 by K1, K1 into K2, K1 plus K2. Okay, 1 minute and you may solve it. First option K1 by K2, right? So the third required reaction we are getting by doing 1 minus 2. So here reaction 3 is reaction 1 minus reaction 2. So therefore K3 is equal to have K1 by K2. Okay, if you subtract these two, you get CO2 gets cancelled, CH4 left side, 2H2O minus H2O, we are subtracting, so minus CO, if you bring right side plus CO, 4H2 minus H2, that is 3H2. So our required equation we are getting by doing 1 minus 2. Next one, Andy. This is given for 4 marks. at a given temperature, consider write the reactions given. Fe2O3 solid plus 3 moles of CO gas, Fe2O3 solid plus 3 moles of CO gas gives 2 moles of iron solid plus 3 moles of CO2 gas. Okay, K1 is equal to 0.05. K1 is equal to 0.05. Okay, so next reaction, 2 moles of CO2 gas plus 2 moles of CO2 gas is in equilibrium with 2 moles of CO gas plus O2 gas. K2 is equal to 2 into 10 power minus 12. 2 into 10 power minus 12. Continuation. The equilibrium constant for the reaction. The equilibrium constant for the reaction. The equilibrium constant for the reaction 2Fe3O2 solid gives 4 moles of iron solid plus 3 moles of O2 is the equilibrium constant for the reaction 2 moles of Fe2O3 solid gives 4 moles of iron plus 3 moles of O2 is options 1 into 10 power minus 13, 2 into 10 power minus 38, 4 into 10 power minus 15, 2 into 10 power minus 24. Check how we are getting third reaction. What are the modifications we have to do? When we are getting third reaction. In our required equation, how many moles of Fe2O3 is there? 2 moles of Fe2O3 is there. That means we have to multiply equation 1 by 2. Equation 1 by 2. Next one, if you multiply equation 1 by 2, here we are getting 6 CO, 4 moles of iron. So here also how many moles of iron we have? 4 moles of iron. Next, if you multiply with 2, 6 moles of CO2 we are getting. 6 moles of CO, 6 moles of CO2 we are getting. Okay, but here we don't have CO and CO2. That to be cancelled. To cancel, we have to multiply equation 2 by how much? 3. If you multiply equation 2 by 3, so 6 CO2 will get 6 CO2, 6 CO2 gets cancelled. Here 6 CO we are getting 6 CO, 6 CO cancelled. 3 moles of O2 we are getting. Okay, so that means when we get reaction 3 reaction 3 is nothing but we have to multiply reaction 1 by what? 2. So 2 into reaction 1 and we have to multiply the reaction reaction 2 by 3. Next we have to add those two or subtract. Add. We have to add. If you add those two, we are getting our required equation. So reaction 3 is 2 into reaction 1 plus 3 into reaction 2. If you have reaction 3 is equal to N1 reaction 1 plus N2 reaction 2, then what is K3? K1 power N1, K2 power N2. So that you may apply here. So K3 is equal to, okay, K1 power how much we will get అండి 2. In the place of N1 what we have 2. K2 power in the place of N2 what we have 3. So K1 power 2, K2 power 3. You must simplify అండి. Which option? Fourth one is not correct. So K3 is equal to K1. K1 means 0.05. 0.05 means we can write it as 5 into 10 power minus 2. K2. 2 into 10 power minus 12 power 3. So 5 square, that is 25 into 10 power minus 4. 2 cube 8 into 10 power minus 36. 25 into 8 and 200. 200 into 10 power minus 40. 200 into 10 power minus 40, that we can write as 2 into 10 power minus 38. 100 we can write as 10 power 2. So 2 minus 40 minus 38. So 2 into 10 power minus 38, that is option 2. Okay, so next one అండి. Right, in the reaction PCl5 gas is in equilibrium with PCl3 gas plus Cl2 gas. In the reaction PCl5 gas gives PCl3 gas plus Cl2 gas. The amounts of PCl5 comma PCl3 and Cl2, the amounts of PCl5, PCl3 and Cl2 are 2 moles each at equilibrium. Are 2 moles each at equilibrium. Continuation, total pressure is 3 atmosphere. Total pressure is 3 atmosphere. Then Kp is equilibrium constant. Then Kp is options 1 atmosphere, 2 atmosphere, 3 atmosphere, 4 atmosphere. What is the value of Kp and all are present 2 moles at equilibrium. What is the expression we have for Kp and Kp is equal to product side partial pressures by reactant side partial pressures. That is partial pressure of PCl3 into partial pressure of Cl2 by partial pressure of PCl5. Okay, how to get partial pressures and if total pressure is given, partial vapor pressure is equal to total vapor pressure into its mole fraction according to Dalton's law. According to Dalton's law, we have partial vapor pressure of a gas is equal to total vapor pressure into its mole fraction. Okay, then what about the partial vapor pressure of PCl3 and if you see the mole fraction of all the gases is same or not? Mole fraction means number of moles by total number of moles. What is the number of moles of each component? 2 moles. So what is the mole fraction we will get for each? 2 by 6. Okay. So partial vapor pressure of PCl3 or partial vapor pressure of Cl2 and partial vapor pressure of PCl5 all are same. All are present how many moles? 2 moles. So mole fraction if you write partial vapor pressure. Okay, partial vapor pressure means total vapor pressure. Total vapor pressure is given how much? 3 and 3. What about the mole fraction and 2 by 6. Partial vapor pressure of all the gases is same and since mole fraction of each gas is same. Mole fraction of each gas is how much? 2 by 6. So 2 ones are 2 threes are. So we are getting 1 and 1 atmosphere. So that if you substitute Kp is equal to, this is 1 atmosphere. Total pressure given in atmosphere. So Kp is equal to partial pressure of PCl3 1 atmosphere, Cl2 1 atmosphere by PCl5 1 atmosphere. Atmosphere gets cancelled. So Kp value is what? 1 atmosphere. Kp value is 1 atmosphere. That is option 1. Okay, last question. Right. Write the reaction. H2 gas plus I2 gas gives 2 moles of HI gas. H2 gas plus I2 gas gives 2 moles of HI gas. Continuation. The reaction is started with 2 moles of each H2 and I2. Reaction is started with 2 moles of each H2 and I2 in 10 liter container. In 10 liter container. Continuation. 1 mole of H2 is found to be reacted. 1 mole of H2 is found to be reacted at equilibrium. 1 mole of H2 is found to be reacted at equilibrium. Calculate Kc. Okay. So this is the reaction given. What is the initial number of moles of H2 and I2 given? 2. Okay. Initially no formation of HI. So that is 0 only. Next, what is given? At equilibrium, how many moles of H2 is found to reacted? 1 mole of H2 is reacted. Okay, out of 2 moles of H2, 1 mole is reacted. That means what is the number of remaining moles of H2 at equilibrium? Remaining number of moles of H2 at equilibrium is 1. Now, if you see the balanced equation, 1 mole of H2 participate in the reaction with 1 mole of I2 to give 2 moles of HI. 1 mole of H2 undergoes reaction with 1 mole of I2 gives rise to 2 moles of HI. So 1 mole of H2 reacted means how many moles of I2 participated? 1 mole of I2 participated. Right? So what is the remaining moles of I2 and at equilibrium? 1. If 1 mole of H2 and 1 mole of I2 participated, what is the number of moles of HI formed at equilibrium? 2 moles. Okay? The number of moles of HI formed at equilibrium is 2 moles. And now we want to calculate Kc. Kc means what? Product side concentrations by reactant side concentrations. Okay. How to give concentration and if number of moles are known to us or not? Yes, number of moles at equilibrium are known to us and volume is also known to us. Okay, concentration is equal to what? Number of moles by volume in liters. concentration is equal to number of moles by volume in liters. So from that we will get Kc is equal to, okay, number of moles of HI 2, number of moles of HI is 2 by concentration, volume and volume is given 10. So 2 by 10 whole power 2, HI power 2 we have. Next, concentration of H2. What is the concentration of H2 at equilibrium? 1. So 1 by 10. Next, concentration of I2. What is concentration of I2? Number of moles at equilibrium is 1. Number of moles by volume in liters, that is 10. So 10 square gets cancelled. So Kc is equal to what we will get? 2 square, that is 4. What is the unit? Can we get any unit? No unit. Here concentration power 2 we have, here also concentration into concentration power 2 we have, gets cancelled, so we don't get any unit. So equilibrium constant value is 4.